Hi, today we'll be looking at a function called the beta function, and it's intimately related to the gamma function. Now, the gamma function has had some notoriety on the internet, but I'm not so sure the beta function has been given its dues. So we're going to see how those two functions are connected, but also how they're connected to this integral right here that John Wallis was studying back in the mid-1650s. I of n equals the integral from 0 to 1 of x minus x squared all to the power n dx. Now, you can evaluate this pretty straightforwardly. This is just a polynomial. The problem is, as n gets larger and larger, it becomes more cumbersome to evaluate the integral. But legend has it that John Wallis evaluated his integral for n equals 0, 1, and 2, obtained 1, 1/6, and 1/30, respectively, and somehow could determine a closed form expression for the integral. Now, you might want to give that a try for a few minutes, see if you notice a pattern here, and determine whether or not you can find a closed form expression for this integral. Anyway, if you can't, we're going to do this together and tie together the beta function, the gamma function, and John Wallis's integral. So let's start. Let's first recall that the gamma function, gamma of p, is the integral from 0 to infinity of e to the minus x times x to the power p minus 1 dx, where p is positive. And interestingly enough, gamma of p plus 1 is just another way to write our factorial function, so this equals p factorial. As well, we're going to define the beta function right here. Beta of the parameters p and q is the integral from 0 to 1 of x to the power p minus 1 times 1 minus x all to the power q minus 1 dx, where p and q are positive. So, how are we going to tie the beta function, the gamma function, and John Wallis's integral together? Well, first we're going to work on the gamma function right here. So we're going to make a substitution and let x be y squared. And if we do that, we obtain dx equals 2y dy. So what does the gamma function become now? Gamma of p equals the integral from, well, when x is 0, so is y. And when x tends to infinity, so does y as well. So those integration bounds don't change. Then we have e to the minus x, which is y squared, times x to the power p minus 1 dx. But dx is 2y dy. Okay, great. So what does this leave us with now? This is the integral from 0 to infinity of e to the minus y squared times y to the power 2p minus 2 times 2y dy. Okay, well this 2 can be brought up front. We'll leave this exponential here. And then this y to the 2p minus 2 times this y will add exponents to give us y to the 2p minus 1 dy. Okay, great. So this is going to come in handy in a short while. But what we're going to do now as well is, with some dummy variables, call gamma of q the same thing as this, but we'll use x's instead of y's. Okay, so why are we doing this? Well, it'll become clear in a while. But the trick here is we're going to multiply gamma of p and gamma of q. So let's see what that gives us. We have this integral here times this integral right here. This is a q. Okay, good. So where do we go from here? Well, let's work on this a bit by tidying it up. So now, what we have is, we'll take this 2 out front to give us 4, and we'll have a double integral from 0 to infinity and 0 to infinity of e to the minus y squared times e to the minus x squared is e to the minus x squared plus y squared times x to the power 2q minus 1 times y to the power 2p minus 1. Okay, good. Well, this looks a little daunting. So what can we do with this? Well, in fact, why don't we look at this integral in polar coordinates? This dx dy is just a little elemental area. We'll call that dA. And recall the following. About polar coordinates as they relate to Cartesian coordinates. We have r squared equals x squared plus y squared. We have x equals r cos theta. And we have y equals r sine theta. Okay, well what we're going to do with this is take x squared plus y squared over here and replace it with r squared. We'll take x and replace it with r cos theta, and we'll take y and replace it with r sine theta. What we have left to show is what dx dy translates into in polar form. Well, let's take a look at a sector in polar coordinates where we have this angle as d theta, this arc length as a, and this side length is r, the radius of the sector. Okay, well, if we extend this out by an amount dr, and now look at the wedge shape that we have, we get an area inside here, a little elemental area, which is essentially a rectangle. So in Cartesian coordinates, it'd have area dx dy. But in polar coordinates, the area would be what? Well, first of all, this arc length A is nothing more than r d theta. And since this is essentially a rectangle, this little shaded green area, its area is A times dr. But since A is r d theta, we have dA equal to r d theta dr, or usually written as r dr d theta. Okay, well that's great. So now, what we have is the following. Coming back down here, gamma of p times gamma of q is nothing more than 4 times the integral from, okay, we'll need to find out our bounds in a moment, so let's just leave that off to the side for a second. But we have e to the minus x squared plus y squared, so r squared, times x here, which is r cos theta, to the power 2q minus 1, times y, which is r sine theta, to the power 2p minus 1. And our dA is r dr d theta. Okay, well now, what are our integration bounds? Well, we're essentially dealing with this function and this, which are fundamentally the same, they'll give you the same graph. Well, what is that really? What we have is this polynomial, y to the power 2p minus 1. Remember, p is positive, so this is at least a linear term, times this decaying exponential. And we're integrating from 0 to infinity. So on the positive half of the x-axis, we have this polynomial, which tends to increase as x grows, but it gets killed off by this exponential, which is decaying. And that will decay down towards 0. So this function, if you were to plot it between 0 and infinity, is just going to give you a graph that you see wholly in the first quadrant. Same argument for this as well. So in the first quadrant, theta runs from 0 to pi over 2, and r runs from 0 to infinity. Okay, good. So now we have gamma of p times gamma of q as this expression right here. So we're going to move this over to the next board and continue with it, manipulate it a little bit more, and see where this leads us. Okay, so here we are now back at the board, reminding ourselves what gamma of p times gamma of q is. So let's work on this a little bit. We get 4 times the integral from 0 to pi over 2, and the 0 to infinity of, well, we have e to the minus r squared times r to the 2q minus 1 times cos to the 2q minus 1 of theta times r to the 2p minus 1 times sine to the 2p minus 1 of theta times r dr d theta. All right, good. Now let's split this up into 2 integrals, one with our theta variables and one with our r variables. So we have 4 times, okay, from 0 to pi over 2, our theta variables are cos to the 2q minus 1 of theta times sine to the 2p minus 1 of theta d theta times the integral from 0 to infinity of our variable r. So we have e to the minus r squared times r to the 2q minus 1 times r to the 2p minus 1 times r over here, dr. Well, this power of r, this power of r, this power of r, we can add exponents and get r to the power 2 times p plus q minus 1. Okay, good. So now we'll have to evaluate or determine what this integral works out to be and what this integral works out to be. Well, if you remember in the very first step where we let x equal y squared, where we made that variable substitution for gamma of p, we had obtained the following. Gamma of p equals twice the integral from 0 to infinity of e to the minus y squared times y to the power 2p minus 1 dy. Well, that's precisely what this gives us, except that we're going to call that gamma of p plus q. The only difference here is, instead of gamma of p, what we have is p plus q. So this integral is half of that, since gamma of p is twice that integral. Okay, so this is half of gamma of p plus q. How about this integral over here? We're going to use this beta function here. And what we're going to do is let x equal cos squared of theta, but that means dx is 2 cos theta times negative sine theta, d theta. And what that also means is 1 minus x is nothing more than, well, 1 minus cos squared of theta, which is sine squared of theta. So putting that together, our beta of p and q is the integral from, okay, we'll find out the bounds in a moment, x to the power p minus 1, well, x is cos squared, times 1 minus x, which is sine squared of theta, to the power q minus 1, dx. And dx is this expression right here. We'll take the negative out front. 2 cos theta sine theta d theta. Okay, good. Well now, what are the integration bounds? Here when x is 0, that gives a value of theta as pi over 2. And here when x is 1, that gives a value for theta of 0. So in the next step, we can reverse these bounds and multiply by negative 1, leaving us simply with the integral from 0 to pi over 2 of, we can extract that 2 out in front as well. And then we're left with this to the power p minus 1, which is cos to the 2p minus 2 of theta. And here we have sine squared to the power q minus 1, which is sine to the 2q minus 2 of theta, times cos theta sine theta d theta. But this cosine and this cosine, we can add powers 2p minus 2 plus 1. So that gives us 2 times the integral from 0 to pi over 2 of cos of 2p minus 1 of theta. And same for sine. Sine of 2q minus 1 of theta d theta. Well, what is that? We'll look back here in green. These match except for this factor of 2. So that means this result here is just twice this. So this is half of the beta function. Okay, great. So notice we have the product of gamma of p and gamma of q equals 4 times half of the beta function times half of the gamma function at p plus q. So let's put this all together now, and we'll see how we can find a closed form expression for John Wallis's integral. Okay, so here we are to wrap things up. So here's where we left off on the last board. We have 2 factors of a half, that's a quarter, times 4, those cancel to give 1. So we get gamma of p times gamma of q equals beta of pq times gamma of p plus q. Well, that means beta of pq is nothing more than gamma of p times gamma of q divided by gamma of p plus q. Okay, great. So how will we tie this to John Wallis's integral? Well, notice here, we can rewrite this integral as the integral from 0 to 1 of, and we'll factor out an x to the power n here. And notice what happens when you compare that with the beta function down here. We have n over here as p minus 1, and n over here as q minus 1. So if we associate n with p minus 1, that gives us p equals n plus 1. And if we associate n with q minus 1, that gives us q equals n plus 1 as well. Well, what does that mean for us? Well, if p and q are each n plus 1, then this p and q gives us n plus 1, n plus 1. So beta of n plus 1 and n plus 1 equals gamma of n plus 1 times gamma of n plus 1 again, divided by, well, p plus q, n plus 1 plus n plus 1 is 2n plus 2. So we get gamma of 2n plus 2. But we can just write that as 2n plus 1 plus 1. And what does that mean for us? It means that beta of n plus 1 comma n plus 1 is, what is gamma of n plus 1? Well, that's n factorial. And then we have another factor of n factorial. We have 2n factorials. So we have n factorial squared divided by, well, we have 2n plus 1 plus 1. So again, that's just 2n plus 1 factorial. And there you have it. Beta of n plus 1 comma n plus 1 equals n factorial squared divided by 2n plus 1 factorial. But we've associated this beta of n plus 1 comma n plus 1 with I of n. So John Wallis's integral is nothing more than n factorial squared divided by 2n plus 1 factorial. And we can give that a try to see if at least these first few results match. When n is 0, we get 0 factorial squared is 1. And down here we get 1 factorial, which is 1. So 1 over 1 is 1. And indeed, I of 0 is 1. When n is 1, we get 1 factorial squared, which is 1. And then down here we get 3 factorial, which is 6. So 1 divided by 6, that does agree. And then I of 2, well, 2 factorial is 2 and squared is 4. 2 times 2 plus 1 is 5. 5 factorial is 120. So 4 divided by 120 is 1 over 30, and that does agree as well. So look at this beautiful connection. We have the gamma function, the beta function, and connected it all to help us find the closed form expression for John Wallis's integral here. And there you have it. We've done it. Thanks for watching.